Now we start. We welcome our honorable attendees as well as our guest, Professor Dr. Martin Smith from the University of Brighton, United Kingdom. At the beginning, I would like to extend my thanks to Dr. Martin for agreeing to cooperate with us and with the University of Baghdad to present this seminar. Today, I think attend with us the scientific assistant to the president of the University of Basra for Oil and Gas, Professor Dr. Ahmad Al-Qarsan. Let me present Dr. Martin's biography in Arabic. اسمحوا لي أقدم السيرة الذاتية للأستاذ المحاضر الأستاذ الدكتور مارتن سميث. هو جيولوجي وبتخصص الجيوكيمياء وعلم المعادن في جامعة برايتون المملكة المتحدة. لديه خبرة أكثر من 20 سنة في مجال الجيوكيمياء التطبيقية على مشاكل جيولوجيا الرواسب المعدنية والهيدروجيولوجي والانفيرومنتال مينرولوجي، وهو جيولوجي معتمد لدى الجمعية الجيولوجية في لندن منذ عام 2012 أكمل دراسة الدكتوراه في سنة 1995 من جامعة ليدز، وعمل لاحقاً في متحف التاريخ الطبيعي في لندن. اهتماماته البحثية حالياً في نشأة المعادن التريس إليمنتس وأصل ترسبات الذهب وأكاسيد الحديد والنحاس، وتأثير تدفق المنطقة غير المشبعة على كيمياء المياه الجوفية، خاصة فيما يتعلق بالأوربان بوليوشن ومعادن الأكسدة والاختزال لتآكل الفولاذ البحري. وهو مسؤول العمل الحقلي لطلبة الدراسات الأولية، حيث قاد العمل الحقلي في أسبانيا وقبرص ومدغشقر، وكما عمل في السويد وروسيا والصين ومدغشقر ومنغوليا، إضافة إلى المملكة المتحدة. Today, Mr. Ahmed Na'ma, a PhD scholarship student, will join me and manage the session. Welcome, Dr. Martin. Kindly present the seminar.
Okay, thank you very much, and thank you very much for inviting me here.
Thank you, Doctor.
As I talk, I will try and present in a minute, but as I talk, if people have questions, if you use the chat bar at the side, I can answer some questions
yes,
as I speak, or we can wait till the end. So I will try and start the slideshow now. Okay, so now can you see the...
Yes.
Good. Okay, well, thank you very much for inviting me to give this seminar. What I want to talk about, and what I've been asked to talk about, is the genesis of iron oxide copper-gold deposits, particularly looking at evidence from the Kiruna district and the Urals in Russia. So this is work that was being conducted with a range of colleagues. I'll just highlight very quickly, Craig Story particularly, who's now at the University of Portsmouth, but colleagues from the Natural History Museum in London, from the University of Alberta, and the original work was supported initially by Anglo-American Mining Company and the European Regional Development Fund GeoRange program, who we worked with in Sweden. So what I want to do really to start with is look at the iron oxide copper-gold class. So this is a group of mineral deposits that were originally defined by Hitzman in 1992. And they're characterized by large amounts of iron oxides associated with copper sulfides and gold, as opposed to the more normal association of large amounts of sulfide minerals. So that was a very different mineral deposit model at the time than was usually used in exploration or in genetic studies. And what had been proposed at the time was that this included two main deposit types. One was massive magnetite apatite deposits, the Kiruna type deposits. So these are an iron resource in their own right. And then the iron oxide copper-gold deposits proper, where we find large amounts of magnetite and hematite associated with copper and gold mineralization. And the link to large amounts of iron oxides meant that a genetic link was proposed between these two deposit types. And the interest was focused on these because some of these systems are extremely large, particularly Olympic Dam in South Australia. So this has huge resources of copper and associated rare earths, some amounts of iron and uranium. So this means they're a very attractive mineral exploration target for the last 20 or 30 years. And there are aspects to them that are also of interest in that the tailings waste is not necessarily as sulfur rich as it might be from a system like a porphyry copper deposit where there are large amounts of pyrite. So there's less acid mine drainage generation. The scale of the system, the two largest mentioned here, Candelaria and Olympic Dam, are around 500 million tons of rock, between 1 and 2% copper, up to 0.6 to 1 gram per ton gold, large amounts of potential other byproduct minerals. So the real interest here is a copper resource that isn't associated with lots of sulfide. But the fact that byproduct gold is possible, in some instances silver as well, makes them very, very interesting.
Excuse me, Martin.
Yes?
This slide is still on the first slide.
Oh, is that? Excuse me, let me just...
Yeah.
Does that change?
Not yet.
Yeah. Excuse me a moment. Apologies, this should be easier, but doesn't seem to be. What I will do, rather than presenting the full screen then, is if I remove thumbnails, I can, and the formatting, I will use, if I change now, can you see now?
Still on the first slide.
Still on the first slide?
Yes.
Apologies. Okay, I will use this screen then. If I change now, can you see the change?
Yeah.
Yeah.
Thank you.
Clear.
Yeah, okay. So I've talked through the introduction and some examples of the deposit types. So what was originally proposed to these deposit types was that they were associated with large-scale igneous activity, either volcanic or plutonic. The source rocks are very oxidized, so iron oxides within the igneous source rocks. There was commonly an association with evaporite minerals or metamorphosed evaporite minerals. They tend to be associated with large-scale faults or smaller splays off larger scale fault structures. They tend to occur either in stratabound layers or in stockwork zones, and they're all replacive. And the defining characteristic, there's an abundance of iron oxide minerals and a relative lack of iron sulfides. But also there's an element association that was quite distinctive about these systems. So they had large amounts of barium, phosphorus, fluorine, the rare earth elements, uranium, silver, molybdenum, cobalt, arsenic, and zinc. So quite a distinctive set of elements that had to be part of any genetic model, but also are useful in exploration because these can be pathfinders for the ore deposits. The associated Kiruna type deposits, the iron oxide apatite deposits, have a number of things in common. They're large bodies of magnetite or hematite, variable amounts of associated apatite and actinolite amphibole, and they're usually associated with a very wide halo of sodium alteration, so making albite, which is overprinted around the deposits by potassium alteration, making K-feldspar and biotite. And the sodium alteration commonly involves scapolite, so this is very distinctive. We have sodium aluminium silicate chloride, so a really salt-rich mineralizing system. And again, the iron oxide apatite deposits are associated with rare earths, uraniums. They've got the same kind of element association. So similar in some ways, but potentially distinct. This led to some real problems with the definition of these deposits. So back in 2001, the Australian Minerals Foundation hosted a conference specifically to look at these deposits and to try and get some agreement as to what they were. The paper volume that was produced from that meeting was reviewed by Larry Minor in 2001. And what he said you could conclude was that all the deposits were associated with igneous rocks and formed from magmatic or magmatic hydrothermal fluids. Most of the deposits are not associated with igneous rocks and didn't form from magmatic fluids. Evaporites, the presence of evaporites was absolutely critical in the formation of all these deposits, but that the largest ones didn't have any evaporites associated with them at all. And finally, that they were related to porphyry copper deposits, carbonatites, and sediment-hosted copper deposits. So really, he was picking holes in the whole argument around this type of deposit, in that it really wasn't a clear consensus as to what they were, and there was no clear idea about how they formed, which meant, moving on from 2001, it was a very rich area for research. People really needed to look at these deposit types to try and decide exactly what we were looking at and exactly how they formed. So there have been several attempts to review that since then. I'll just mention one here, which is Williams et al. In 2005, who said there was a very clear spatial association between iron oxide apatite and IOCG deposits. They were always associated with alkali metasomatism, so sodium and potassium. They always had the element enrichments, so the same suite of elements always occurred, but they had a wide time distribution. They were geologically diverse, but the genetic models always included very complex hydrothermal brines, so very, very salt-rich hydrothermal solutions, possibly from multiple different sources. And there may have been a role for mixing of sulfur-poor, metal-rich brines with sulfur-bearing fluids, which resulted in the copper sulfide mineralization. So this was a clearer idea of what exactly we're looking at, but it left some problems. The main one being the actual iron oxide apatite deposits themselves, the Kiruna type deposits, because the formation deposits there are very, very hotly debated. So in terms of formation models, people have proposed that the iron oxide apatite deposits crystallized from an iron oxide magma, and that's been proposed at Kiruna and in Chile. It's been suggested that they're the result of submarine hydrothermal sedimentation, or that they're formed by the metasomatic replacement of volcanic rocks. So there's a real fundamental geological question here, and it's still debated. People still talk about iron oxide magmas forming Kiruna type deposits. So there's a major geological process and a major iron resource that may be linked also to the copper and gold deposits that needs further research. So the questions we set out to answer when we started looking at this deposit type were, how do iron oxide apatite deposits form, the Kiruna type deposits? How are they linked to the iron oxide copper-gold deposits? And we looked at temporal links using uranium-lead dating of titanite, and chemical links by looking at fluid inclusions and what sort of hydrothermal fluids were associated with these mineral deposit types. We also concerned ourselves with where the metals could be coming from. So we looked at the rare earth elements within different mineral phases, but particularly titanite again, and also neodymium isotope analyses of some of these minerals. And finally, we concerned ourselves a little bit with exactly how metals were transported through these systems, with the overall aim of trying to improve genetic models for the deposit type and using that to help exploration for this type of mineral deposit, particularly in Sweden, which is where we started working. And this is just to summarize this is possibly the latest review of these different deposit types from Mark Barton and his co-workers in 2014. And they started to recognize that there were potentially 3 different types of systems. Systems that might be related to porphyry copper deposits, where subvolcanic intrusions released sodium chloride-rich solutions, which carried iron oxides into the deeper subsurface, and then into the shallow subsurface where they caused copper and gold mineralization. They could be related to surface-derived brines, so continental evaporitic brines where we get very, very high salinities that are then being drawn down into hydrothermal circulation systems, and again, carrying iron oxides and causing iron oxide and copper-gold mineralization. And finally, the very deep basin fluids from the metamorphism and breakdown of evaporite beds might release sodium chloride-rich brines, again, into fault-controlled hydrothermal systems that cause copper, gold, and iron oxide mineralization. So this is the kind of framework we're looking in. Where we're looking is, well, now it's these types of deposits have been recognized globally. So they're down through Iran in this area, the BAF deposits, they're in Turkey, they've been recognized in the United States, they've been recognized in South America, Australia. What I want to look at particularly is the areas that I've worked on, which is the southern Urals and the North Baltic, the Swedish deposits. And I'm going to start by going to the southern Urals, which are perhaps less well known as an iron oxide copper gold system, but the deposits there are late Paleozoic to Mesozoic in age. They might actually tell us something very useful about the deposit types because they're better preserved than some of the older systems. They're interesting to look at. The Turgai deposits, these are the southern Urals deposits. So what's shown on this diagram is the mass of rock in tons that is mineralized and the weight % iron at the side. So the contours here show the tonnage, the number of tons of contained metal. So if we look at Kiruna Vara up here, it's one of the biggest hydrothermal iron systems, if we accept that it's hydrothermal, and I'll try and convince you of that as we go along. Biggest iron mineralized systems that there is, alongside Marcona, Athk, and Malmberget is another Swedish deposit. But if we take these southern Ural deposits, the Turgai area deposits, and add them together, they have around the same tonnage. They're the same sort of size as the Kiruna system. So we're looking at 1 billion tons of contained iron. These are very, very large iron resources. So this is where we're working. So we've got the Ural Mountains. It's a Devonian collisional orogeny overlain by Carboniferous to Mesozoic sediments. And what we have here, we've got the main Ural system. Magnitogorsk here is a very, very large iron mineralized system. But off into this area in Kazakhstan, we have a volcanic arc, probably from the opposite side of the mountain building period to the Magnitogorsk arc over here. And this features some very, very large iron mineralized systems. So that's what we're going to look at. And typically they'll look like this. There are 3 major systems there, Sabai, Sokolov, and Kachar. And this is a map of the Kachar deposit in a cross-section, just illustrating what the typical geology of these systems is. So we have granitoid intrusions. They're overlain by Carboniferous limestones, interbedded with volcanic rocks. And it's within those limestone and volcanic beds that we see very large lenses of magnetite developed, and they're surrounded by a halo of pyroxene skarn, which wouldn't be so unusual if we're looking at a limestone replacement system around an intrusion, but also large amounts of scapolite. So we have this link to these very sodium-rich hydrothermal systems. And that scapolite gives us a link to the Kiruna type iron oxide apatite systems. There are some big similarities between these iron deposits and those of northern Sweden. This is what some of these rock systems look like. So we have extremely coarse pyroxene, and this is diopside. So it's calcium, magnesium, iron pyroxene, typical for skarns, associated with magnetite. We get later stage hematite. So we've got some beautiful specular hematite here, filling a cavity in a large magnetite body, alongside calcite and very late chalcopyrite. So we have a small amount of copper mineralization here. These deposits aren't economic for copper. They occur in breccias, and we've got brecciated volcanic rock here, cemented by magnetite with the development of grossular andradite garnet, GT there, and epidote. And around those bodies, still with iron oxide mineralization, so we have magnetite and hematite down the side of this sample, but we've got very coarse-grained scapolite developed, so sodium, aluminium, silicate chloride, really, really salt-rich systems, and then in this case some late-stage zeolites. That mineralization and skarn-like, so limestone replacement around a granite alteration type, those mineralization are associated with some really distinctive accessory minerals. So we have apatite, as we have in the Kiruna type systems. We have titanite, calcium titanium silicate, as we have in the Kiruna type systems. And then we have the late stage zeolites as well. So we have some clear parallels to the Kiruna type systems. What becomes really important now is at Kiruna, the argument has been around whether they are hydrothermal replacement deposits or actually some form of iron oxide magma that form those deposits. Well, within the Turgay system, we have absolutely definitive evidence that these deposits replaced limestone. You can see here we have magnetite. The pale green is diopside pyroxene, but in this case, we've got a fossil coral preserved in diopside pyroxene. So essentially, the mineralizing system that's made the iron oxide deposit that's produced the typical metasomatic limestone minerals of diopside and garnet has perfectly replaced the original limestone. So this is definitely a hydrothermal replacement deposit. And we can go further, we can see features like this. So in this case, we have a cut slab through some magnetite. We have garnet, as we'd expect to see in a limestone hosted skarn down here. We have magnetite. It's cut by an albite vein. So again, we have evidence for very sodium rich systems. And in the surrounding magnetite, we've still got goniatite, so ammonoid fossils preserved. In this case, we've got magnetite replacement of the whole rock, but the fossil itself has been replaced by chalcopyrite. And you can see the same sorts of features, but cut in a different direction down here. So there is no real doubt that these huge magnetite systems in the southern Urals have some very close parallels to the iron oxide systems in northern Sweden, but they are very, very clearly replacive. Around the limestone units, we get volcanic rocks preserved, but we still see in these breccias within the volcanic rocks, the matrix to the breccia is scapolite. So again, sodium, aluminium, silicate chloride, a very, very salt-rich system to make scapolite. And we can see the volcanic clasts are actually being replaced by magnetite. So whatever fluids formed these systems in the southern Urals, they were corrosive enough to dissolve up an aluminosilicate rock and replace it with iron oxides. And that's a really key piece of evidence as to how some of these systems must have formed. We can even go down to microscale. This isn't the best diagram, apologies, particularly when it's projected like this. But at the microscale, we can see a fossil coral here, but it's preserved not just in limestone, but in quartz and amphibole. So the high temperature hydrothermal mineral assemblage is replacing perfectly the limestone system. We've got our normal skarn type limestone alteration system with garnet and epidote. And you can see this in an electron microscope photograph here. This is a backscattered electron image. So the grey contrast is atomic number, contrast is atomic number, it's chemistry. Excuse me a moment, we had something peculiar with the sound there. So we have calcite, we have diopside pyroxene, we have garnet, and we have amphibole. So what we'd expect in a typical limestone hosted skarn, but in areas we get areas like this. So again, this is an electron microscope photograph, but here we have apatite, albite, and magnetite. So a mineral assemblage that wouldn't look out of place in a Kiruna type deposit. So we have links between a limestone hosted skarn system and the iron oxide apatite systems. Very briefly, we have some geochemistry on those rocks. So what these graphs are showing is the oxygen stable isotope composition of different minerals and the sulfur stable isotope composition of different minerals. These are corrected for mineral water fractionation at different temperatures. But the main point here is that the magnetite oxygen isotope signature fits with magmatic water mixed with marine limestone. It doesn't fit with any other source of potential hydrothermal fluid. These are hydrothermal fluids that have come off crystallizing granitoids and made iron oxides in the surrounding limestone. When we go to the sulfides, we see the same thing. So this is the sulfur stable isotope ratio. And the sulfur stable isotopes strongly reflect magmatic sources, modified a little bit by the sulfide deposition. So all the evidence points to these magnetite systems in the southern Urals being formed from magmatic sourced, very saline hydrothermal fluids. So we have an indication there of the potential way that the iron oxide apatite deposits formed in places like Kiruna. And I would argue very strongly that these are definitely metasomatic replacement deposits. When we look at places like Kiruna, we have to think about that. We have to think in that way, that these are metasomatic replacement. They're probably not anything to do with oxide magmas. That's not to say oxide magmas don't exist elsewhere, but to make 2 billion tons of iron ore, we need a big hydrothermal system. That's how we're going to do it. So the more famous systems actually occur in northern Sweden. So the inset map here is Scandinavia. We have the Caledonian orogeny up here in Norway, and we have Finland, which are largely Archean rocks and Karelian rocks, and then we have the Sveco-Karelian. So this is metamorphosed volcanic and sedimentary rocks of about 1.9 down to about 1.7 billion years old.
Excuse me.
Yes, sorry.
Can you share your desktop with us, because we cannot see the pictures or your desktop?
You can't see the slides again.
We just can't see.
It's okay now.
Okay. Can you see them now?
Yes, it's okay.
Okay. So I'm just saying, this is the Kiruna area in northern Sweden. So we're looking at Paleoproterozoic igneous and sedimentary rocks, volcanic and sedimentary rocks, overlying Archean gneisses. And this is a zoom into the Kiruna district. So Kiruna town, the large iron deposits at Kiruna are here. In the northern area here, we have Archean rocks, gneisses. The dark green on this side of the map are Caledonian rocks. So these are the Norwegian mountain ranges. And overlying the Archean gneiss, we have in pale green basic volcanic rocks called the greenstone group. And in yellow, orange, we have acid to intermediate volcanic rocks called the porphyry group. So two broad groups of volcanic rocks. And then they're intruded by a large range of granitoids. So we have two phases of granitoids, one at about 1.8 billion years old, pink ones, and one at about 1.9 billion years old, the darker coloured granitoids mapped through there. So this is the context of where we're working. The whole area is cut by some very large shear zones. So you have shear zone system coming down through Kiruna, and a shear zone system that comes down, and there's a second large iron deposit at Malmberget here. And this shear zone here is called the Nautanen deformation zone. So what we see is the large iron deposits at Kiruna and Malmberget. There are smaller iron deposits at places like Svappavaara, and there are small iron deposits all over this area. And then there are copper deposits around Kiruna, and also copper deposits around Malmberget and Jalavari down here. So we have this association between the iron oxide apatite deposits and copper deposition.
Excuse me, doctor. Sorry, still we cannot see the slides. It seems that you didn't share the PowerPoint.
Some people are saying, can you see? Okay.
Now we cannot see the slides.
Excuse me, it is okay now. Just please make pin on the slide so you can show, you can see the all the slides.
Can you see the slides now?
Yeah, I can see it.
Can
Yes,
everybody
we can.
else?
Yeah,
We
I
can
think,
see.
yeah, I think the program.
Okay, yeah. Now it's okay. Okay, thank you.
So you can see the slides now, yeah?
Yes,
Yeah.
yes.
Yeah.
Continue.
Okay, great.
Continue.
So we're going to look first around Kiruna area. Well, the first thing is all across this area, we see regional sodium alteration. So we see development of scapolite and albite. This is the edge of a diorite intrusion. You can see part of the original igneous texture here. And around it, we've got a breccia of sedimentary rocks with probably originally an igneous matrix, but everything has been altered to very dark amphibole, and the very white grey material is scapolite and albite. So across the area, we see extensive evidence for this sodium-rich alteration of the rocks. So if we zoom in on Kiruna, this is the very famous iron oxide apatite deposit. This is the system that gave them the name Kiruna-type deposits. So what we see here, in the northwest of this little map, we have granitoids. The green coming down this side is metabasic rocks, the greenstone group. Then overlying that, we have a sequence of what's termed the porphyry group. So we have conglomerate that sits immediately on top of the greenstone group, then andesites, rhyolites and rhyodacite, and then quartzite sediments up here. And at the junction between, at the top of the andesite, trachyandesite system, we have magnetite deposits all the way down here. This is the Kiruna body, coming up to Lusavara here, which is a faulted extension of the same body. And then around that, we have also some more hematite-rich iron oxide deposits at places like Nuctus, Henry, and Rectorn. So these are similar to Kiruna, much smaller and with a lot more hematite in. So we have a lot of magnetite mineralization around here and a smaller amount of hematite mineralization. But if you look at the scale down here, the magnetite layer that forms the Kiruna body is probably around 2 kilometers long. This is a very, very large system. In the surroundings to that, we have Viscaria, Patavara, and Rakuriyavi. So these are copper deposits. They're all also very iron oxide rich, but Viscaria and Patavara have been mined for copper. So these are examples of the iron oxide copper-gold class with, as we'd expect, this spatial association. They're close to the iron oxide deposits at Kiruna. And this is what some of these materials look like. So this is the summit of Kiruna Hill, just outside the actual magnetite mine. And the margins of this is the margin of the magnetite body. So what you can see here is massive magnetite, large amounts of iron oxide there. And the margin of the body is brecciated lava flow cemented by magnetite in this case. If we go to areas where we have away from the brecciated margins, this is Nuctus, which is one of the smaller iron oxide bodies. You can see magnetite, and we've got very coarse grain apatite developed in that area. The iron oxide bodies do have a small amount of potential link to copper. There's some malachite staining seen in magnetite here at the place called Rectorn. But they also have in the surrounding metavolcanics a lot of quartz veining formed. So it is possible to find definitely hydrothermal features around these bodies. The copper bodies themselves look a little different. So this is Patavara. This was a copper mine. There's very significant quartz and anchorite, so iron carbonate veining in this case, associated with copper mineralization. We still see coarse magnetite veins, but in this case associated with actinolite and small amounts of calcite. And the surrounding rocks at this site are albite altered. And then we see, again, scapolite alteration. So this is a dike that cuts the Patavara deposit, but it's strongly altered to scapolite, sodium aluminium silicate chloride. And all of these are associated with magnetite breccias and quartz magnetite veins with chalcopyrite developed in them. So this is the typical iron oxide copper-gold mineralization of the area. Rakuri Yavi was a more recent discovery in the early 2000s, but it gives a really typical example of what we'd expect to see for this style of iron oxide copper-gold mineralization. So we have brecciated magnetite with small amounts of calcite and apatite, and it's cemented by chalcopyrite. So this is what the mining companies would like to find in this area. This was an animated slide, so excuse me a moment. And surrounding that, we see the less mineralized breccias. So we see breccias of volcanic rock, but you can see here the clasts are starting to be replaced by a hydrothermal assemblage, and that includes magnetite. So we have direct replacement of silicate volcanic clasts by magnetite until we eventually develop mixed lithic magnetite breccias, and then finally a magnetite breccia cemented with chalcopyrite. So this is the iron oxide copper gold mineralization style, clearly hydrothermal in these cases. The other major mining area in the Kiruna district is sub-town of Yalavari, which is down here, and the mine of Mamberia, which is another major iron ore mine. So this is a magnetite hematite mineralized system, but at Mamberia it's much more deformed. It's been metamorphosed and deformed to a much greater extent than at Kiruna, and that's possibly due to the proximity of the Mountain Deformation Zone. This is a major shear zone that cuts across the area, and as that shear zone system comes out of the granites and into the metamorphosed volcanic and sedimentary sequence, we get development of lots and lots of small copper deposits at Nautanen. And at this point down here, this single red dot, which is a copper gold deposit, is Aitik, which is Europe's largest copper deposit, or it was at the time. So a really significant copper mineralizing system, again, close to an iron oxide system. You can see the differences in the rocks here, though. So this is Josephina mine, which is part of the Mamberia system. And we've got magnetite, and we have apatite and small amounts of carbonate here as well. But you can see we've got a strongly foliated texture. These ores have been deformed. And you can see it from a distance here at Mamberia, where we have the shearing out of metavolcanic rocks into the margins of the magnetite iron oxide body. Again, lots of quartz veining in the surrounding rocks. And we see the strong deformation also developed around the copper deposits. This photograph of these schists is from Nautanen. So the first thing we did when we started working in Sweden was to think about the geochronology and what could we actually say about the age of these ores. They're always associated with the development of titanite, calcium titanium silicate, in the wall rocks, and sometimes intergrown with the magnetite. So we targeted titanite as something that we could use for uranium lead dating, and we used a laser ablation technique because these are very complicated grains. And you can see this example here. This is from just outside the ore zone at Lusavara. So this is part of the Kiruna-Vara system, an iron oxide apatite deposit. All of that image that isn't completely black is titanite. But you can see here we have a core to the grain. So this is defined by a difference in the iron content of the titanite, and we have a strongly corroded iron poor titanite core. And that's overgrown by an uncorroded and well-zoned, growth-zoned titanite crystal, which is more iron rich. So what's been done here, you can see these features. The circles are laser ablation pits for trace element analyses, and the lozenge shapes are where a laser has been rastered to take out a larger amount of material, the uranium lead analyses. So we've tried to age date the core of these crystals and the rim of these crystals, and to find differences in the geochemistry at different parts of the crystal. So again, this was intended to be an animated slide, but I will present it like this. So this is the data from that crystal. So what we have here is the isotopic ratios of uranium and lead, two different uranium isotopes, two different lead isotopes, and we have the Concordia line. So if we determine a radiometric age from the two different uranium-lead ratios, when they agree, they should lie along this line. And it's a curve because they have different isotopic decay rates. So each of these circles is the error on an individual laser ablation analyses. So what we see here is a concentration of analyses that define an age that fits with what is the known age for the magnetite mineralization at Kiruna, which is 1,875 million years old. What we found in the titanite cores in blue is that the titanite in those rocks had formed much earlier than that, about 2 billion years old. So these are much older. So the first point we can get from this is that the actual hydrothermal mineralization at Kiruna is younger than its host rocks. It's not syngenetic, it's later. And that's backed up by the fact that the core and the rim of those titanite crystals have very, very different rare earth contents. So this is a chondrite normalized rare earth plot, and you can see the rim has a light rare earth enriched profile, which matches the actual Kiruna deposits themselves, and a relatively flat heavy rare earth profile. And the core has a much lower rare earth abundance and a very different pattern. So this is two different generations of titanite, one relating to the host rocks and one relating to the hydrothermal mineralization event. So this really doesn't fit with the Kiruna deposits being part of the volcanic sequence as some kind of magnetite magma. They are later deposits. And just to reinforce that, we checked some other deposit types. This is Grooveberryite, which is a smaller iron oxide apatite deposit, but associated with more copper mineralization, more chalcopyrite present. And in this case, we have rutile, titanium oxide, overgrown by iron-poor corroded titanite, but with a rim of euhedral titanite crystals, which are slightly more iron-rich. And when we use the laser system to determine the uranium-lead isotope ratios in this again, we get the same relationship. We get mineralization at around, in this case, 1,820 million years, and a core that is older than 2 billion years old. And again, we get a distinction in the rare earth pattern, so that the rims are much more rare earth rich and reflect what was going on with the mineralization, but the cores reflect the behavior of the host rocks. So these are epigenetic deposits. They're later than the host rocks. And we see it elsewhere. I'm not going to talk through every single one of these, but we see the same relationship at Valcommon. And at Valcommon, we get a whole range of uranium lead ages because the deposits have been metamorphosed repeatedly, probably down to about 1.7 billion years old. So if we pull that all together with all the information from the literature, this is a histogram, or two histograms, showing ages from the literature reported for magmatic rocks and from mineralization in northern Sweden. So what we see in the magmatic rocks is we see the Archean gneisses, we see the greenstones that are associated with those gneisses, metamorphosed basalts. We see a later generation of basic igneous rocks associated with the breakup of the Archean craton. And then we see what's termed the greenstone group, basic rocks we see around Kiruna. The new ages for the porphyry group, which are older than the major granitoids that occur in the Kiruna area. And then finally, we see the latest stage of granite formation. So when we look at the ages of mineralization, the iron oxide apatite deposits are similar in age to the main granodiorites, the I-type subduction-related granitoids. And we see some spread in ages, they're not all forming at the same time. And then we see at places like Aitik, the most copper-rich systems have been metamorphosed and are forming around the same time as the latest post-orogenic granitoids. So we've got a whole sequence of different times going on. And we can fit, in terms of the breakup of the original Archean craton, basic magmatism, and then a shift back to subduction. And it's the subduction stage where we see the iron oxide apatite and the IOCG mineralization coming in. So what we wanted to think about then was, if we have different deposits related to different parts of that time sequence, what we want to think about is where those metals came from. So we've also looked at the neodymium isotope ratio. So people may be familiar with this, I'll go for it anyway, but samarium decays to neodymium. And what we tend to see is that samarium is compatible in the mantle, so the mantle develops more 143 neodymium by radioactive decay than things that have been extracted from the mantle. So what we can look at is, are we taking our metal systems off, things that have been extracted from enriched mantle, there are new basic igneous rocks feeding the copper mineralization, or are they extracted from things that have come from older mantle type systems? So what we looked at here is the neodymium isotope ratio. We've got the various curves people have suggested for the evolution of neodymium isotope ratios in the upper mantle. We've got the estimate of bulk earth, the chondritic uniform reservoir here at 0. And what we can see is the Archean basement rocks, the ancient gneisses, should give us much more 143 neodymium depleted isotope ratios. So we don't have any relationship really between the ore deposits and the ancient gneissic basement. Where the ore deposit titanite neodymium does match igneous rocks is that they appear to have the same neodymium isotope composition as the major granitoids that have intruded the sequence. So these the rare earths look like they are derived from those granitoids, except for at Nowland. So this is the deformed, very copper-rich system. And in that case, the rare earths, the neodymium and samarium, appear to derive from the basic rocks. So the copper-rich systems have much more interaction with basic volcanic rocks, whereas the iron-rich systems have more relationship to the granitic rocks. If we look at the model ages of those, so these are the estimated ages of when the neodymium in those titanite crystals separated from the depleted mantle. We can see that what we're seeing is melting of ancient greenstone rocks, so iron-rich source rocks, to generate the granitide rocks that are forming down here. But younger basaltic rocks are feeding into the more copper-rich systems. So our overall conclusion from this is that the iron oxide apatite systems are forming from hydrothermal fluids related to the intrusion of the granitoids during subduction system, and they've all recycled metals by remelting the old greenstone crust. These are the model ages of the neodymium isotope ratios. The more copper-rich mineralization has extracted metals either via melting or hydrothermal circulation from more recent greenstone group basaltic rocks. So the younger the basaltic rocks involved in the melting and remobilization of bits of crust, the more copper we get in the system, basically. So what we can conclude on metal source is that the porphyry group is older than we originally thought. with rare earths that reflect the host volcanic rocks. And that probably means that the porphyry group are intermediate and acid igneous rocks, are more related to the basic rocks of the greenstone group. But the mineralization came in with the intrusion of the Sphecophanean granitoids, the subduction system granitoids. And then we had additional copper added to the most copper-rich deposits during metamorphism and late-stage alteration, where the late-stage post-orogenic granites caused hydrothermal systems to leach metals from younger basic igneous rocks. So we get a picture of why we get differences in the metal content of some of these fluids. But I've said there that we concluded that these fluids were hydrothermal. These systems were all hydrothermal. So the next question we wanted to answer was, what were those solutions? So there are quartz veins associated with all these deposits. There are problems with the iron oxide apatite deposits because the quartz isn't in the ground with the magnetite. We can't say it's definitely the same age. But where the quartz veins cut magnetite, there's no alteration. So they were magnetite saturated. They weren't out of equilibrium with magnetite. So they are presumably related to the magnetite deposition. So in each of these examples, these are two iron oxide apatite deposits, Kiruna and Nuctus. And in each case, we can see a fluid inclusion with a vapor bubble, and they've got halite crystals in. These are crystals of sodium chloride. And at Kiruna here, you can see every single fluid inclusion we can see has a single cube in it. So these are brines that were trapped at high temperature and pressures, and as they cooled, they crystallized sodium chloride into these small pockets of fluids trapped in the quartz crystals. When we go to the copper-gold deposits, they also have crystals of halite in the fluid inclusions, but they have much more complex daughter mineral assemblages as well. So we see crystals of lots of different salts in these solutions. But we can see that what we've got here is a complex mixture of brines. Everything is much, much saltier than seawater. When we go to the copper-rich systems that have been metamorphosed, so this is Nautanen, we still see the sodium chloride-rich brines. But overprinting that in fractures and secondary trails cutting the quartz crystals, we see water plus carbon dioxide plus vapor inclusions. So after the high salinity fluids that form the iron oxide apatite deposits and some of the copper mineralization, we get a second stage of hydrothermal mineralization that is much less saline. We can't see any salt crystals here, and it's carbon dioxide rich. So we've got a major change in the hydrothermal solution composition. When we look at the composition of those inclusions, so this is microthermometric data. We've measured either the melting temperature of ice or of water carbon dioxide clathrate, or we've measured the dissolution temperature of sodium chloride and used that to calculate the salinity, and we've measured the disappearance of the vapor bubble, the homogenization temperature from liquid plus vapor to just liquid. So what we see is, in the iron oxide apatite deposits, that we're about 30 to 48% salts. So they must be at very high temperature to be that saline. And they're relatively sodium chloride rich. We don't see any evidence for calcium chloride from measuring the hydrohalite, the intermediate water salt compound, melting temperature. In the iron oxide copper-gold deposits, we see some similar fluids, 30 to 48% salts, but we also see these much more complex brines that actually reach the point of having more salt than water in them. They're incredibly saline, up to 68% sodium chloride equivalent. Those are still very sodium chloride dominated, but we see some fluid inclusions, late stage, that are very calcium rich. They actually crystallize hydrohalite and it melts at relatively high temperature. So we can say that there must be a lot of calcium in these solutions. So we've got a complex mixture of solutions that have interacted with these deposits. if we go to the copper-rich systems on the Newton and deformation zone, we see the same range of fluids of which we saw in the iron oxide copper gold deposits. We also see the calcium-rich solutions, late-stage calcium-rich solutions, but we also get the carbon dioxide water solutions that are much lower salinity. So what we wanted to ask then is, which of these fluids do we think are moving iron as a hydrothermal fluid? If you look at the salinities here, these are at high temperature, these are going to be incredibly corrosive. These are responsible for the replacement reactions. So which of these is carrying the iron, and where are we carrying copper? So again, we turn to laser ablation inductively coupled plasma mass spectrometry, work that we did with Leeds University, and the uranium lead dating was done at the Natural History Museum in London. And we looked at the chemistry of individual fluid inclusions. The first thing we're concerned about was actually looking at where the salts had come from. So this isn't laser ablation data, my apologies. This is where we've crushed bulk quartz samples and then leached them to release the salts so that we can analyze the chlorine-bromine ratio in solution. And also with Sarah Gleason, who was at University of Alberta at the time, is now at Potsdam in Germany, the chlorine stable isotope ratio. And what we see is that these solutions are completely different salinities and chlorine-bromine ratios to seawater. So we think they're not surface-derived hydrothermal fluids, but also very, very different from what people have measured in volcanic gases. They're not typical magmatic fluids either. They've got much more chlorine in them compared to bromine. When we look at the chlorine stable isotope ratio, the shaded box here is showing where typical igneous systems lie, and we're actually light chlorine, so chlorine 35 enriched relative to chlorine 37. They're isotopically light, so they don't look like typical magmatic fluids there either. So we have an initial problem as to where the salts in these solutions came from. And the most likely explanation is that we've dissolved halite from some source, potentially evaporites. So we start with a magmatic sourced brine from the granitoids, and it becomes more saline by interacting with evaporite layers in the metasedimentary sequence. It then loses chlorine to the rocks. We lose chlorine 37, the isotopically heavy chlorine, into minerals like scapolite and biotite, and progressively paint an isotopically lighter solution. So we've got a really complex origin of the hydrothermal solutions that made these deposits. But however we get this incredibly high salt content, something that's this saline is going to carry a lot of metal. We backed this up later on by looking at the actual scapolite, and what we can see is the fluid inclusion data we saw was down in this area on this diagram. This is the chlorine isotope ratio again, but the solid phase is all heavier, isotopically heavier. So this has caused this reduction in the chlorine stable isotope ratio in the hydrothermal fluids. We have a model that fits together. We've lost chlorine into minerals like scapolite and biotite. So this is where we turn to the laser ablation ICP-MS data. And in this case, I've plotted salinity against the reconstructed metal content of individual fluid inclusions. So what we can see here, dark filled symbols here are iron oxide apatite and the normal iron oxide copper-gold deposits. And the paler triangular symbols down here are the copper-rich, the carbon dioxide bearing copper-rich solution. So the carbon dioxide bearing solutions from the copper-rich deposits on the Newton and deformation zone. So the first thing to note is that a metal like iron, its concentration goes up perfectly with the salinity. So we know iron binds to chloride and goes into solution as iron chloride complex ions. And we're up to nearly the same concentration of iron as sodium in some of these brines. They're iron chloride solutions. And that gives us a link potentially to the idea of these as magmatic fluids. They are more salt than water in some instances, and they have very high iron chloride concentrations. And that is perfectly in line with iron following chlorine. We've got some slight differences in the lower salinity inclusions that are slightly more iron rich than we'd predict from that trend. If we look at a metal like copper, though, these are the iron oxide apatite bodies, and they've got the lowest copper concentrations we see. As we go up salinity to the iron oxide-copper-gold solutions, they've still got relatively low copper contents. But the carbon dioxide low salinity solutions that we see interacting with an Erbsen deformation zone at late stage has some of the highest copper concentrations. So the copper is not necessarily coming with the same hydrothermal fluids that made the iron oxide bodies. We've got here copper coming in at a different stage of the hydrothermal system, different fluids, and reacting with the earlier formed magnetite and hematite to deposit copper sulfides. And if we look at precious metals, the data aren't so good because they're there at much lower concentrations, but gold has the same behavior. It's higher in the low salinity fluid inclusions than it is in the iron oxide apatite associated fluid inclusions. And the same again for silver. It's higher in the high salinity inclusions, but also very high in the low salinity inclusions. So not all these metals are being transported by chloride. Something else is going on. We can't, or we couldn't analyze sulfur by the same method of laser ablation when we did this work. There are groups now that have managed to measure sulfur content of fluid inclusions by laser ablation. We measured sulfur by crushing and leaching the quartz, so looking at bulk samples. But when we do that, measure the copper content as well, the copper correlates very strongly with the sulfur content. Copper isn't following the highly saline chloride brines, it's following the solutions with the higher sulfur content. And the more salt we add to a solution, the less gas we can dissolve in it. So when we have very highly saline brines, we can have very low sulfur contents because sulfur dioxide and hydrogen sulfide are driven off from the solution, particularly when we've got separation of carbon dioxide rich solutions, which we have in the latest stage brines. So if we look at some theoretical data, so this is the complex ion forming reaction between a metal and hydrogen sulfide. So it enhances the solubility of metals as bisulfide complexes. We've got the same reaction, the same reaction here for metal plus chloride. And what we've got is the equilibrium constants for these reactions plotted up the side. What you can see is that at high temperature, copper chloride, gold chloride, silver chloride do not form really strong complex ions. Metals like iron do, they form much stronger complex ions at high temperature. So metals like iron, lead, and zinc will be favored by transporting chloride-rich brines. But metals like gold, silver, and copper are going to follow the sulfur. They're going to be transported where we have bisulfide in the system. And any process that reduces the activity of the sulfide or adds more sulfur to the system will deposit copper sulfides. So, in terms of the transport of the metals, the main transition metal species follow the salinity. We're bringing lots and lots of iron in with those very chloride-rich brines. And the behavior of the chlorine-stable isotopes suggests that they're actually being leached from the surrounding rock during sodic alteration and then being redeposited into form the main iron and copper deposits. We then got modification of some of those deposits and an increase in the copper content because lower salinity fluids associated with the later stage granites are transporting copper as bisulfide, potentially extracted from the younger basic rocks, and these are increasing the copper content of the deposits at Naughton and Nautic during later stage metamorphic alteration of the deposits. And we can say that because we know something about where the metals have been leached from as well, from looking at the neodymium isotope data. So the overall conclusion, in the Kiruna district, the iron oxide apatite mineralization wasn't syngenetic with its host rocks. And it seems very likely it was hydrothermal in origin, not related to oxide magmas. And that is still a hot debate. You could have speakers from Sweden who would disagree with me there. So it's something that still needs looking at. We've got a change in the tectonic history of the area, but we've also got multiple hydrothermal fluid sources that are adding copper at later stages in the initial formation of deposits. So a really complex system that evolved over millions of years with different hydrothermal solutions interacting at similar sites at different times. What I'll conclude there is that's evidence from just 2 sites, and there are lots of arguments about precisely what goes on with the Kiruna type iron oxide apatite deposits. Is there really a single genetic model is still a problem. We also need to understand why we get differences in salinity and different mineralizing fluids between iron and copper in this system. Why is the iron oxide and the copper mineralization separated? And are they related? We've traced metal sources using the rare earths, but we haven't traced copper directly, which is a concern, and how that relates to the regional sodium metasomatism. And through all this, what we say everywhere when we look at the fluid inclusions is these late stage calcium dominated brines. And we don't know really what role they have in ore deposition yet. So I'll end there. I hope that's everyone's been able to follow that. And if there are any questions at all, please ask me.
Thank you, Dr. Martin. Thank you for this wonderful seminar. We appreciate your efforts, Dr. Martin, very much. Thank you. Thank you. Thank you very much. And we hope to meet again. Honored to meet you. Thank you very much.
Thank you very much for the opportunity to speak. And thank you very much for everyone for attending. That was a very big audience for an online presentation, so I'm very impressed. Thank you very much.
Thank you and goodbye.
Thank you, Dr. Martin.